Good day, welcome to 124. We are going to learn a lot in this course. So let's start with chapter 1, vectors, or more specifically, algebraic vectors. So why do we need algebraic vectors? Well, we need new objects to describe the world or space that we live in. And sometimes data is a row of numbers, and a nice way to describe a row of numbers is by using a vector. Alright, so without any further ado, let n be an element of n, so n is a natural number. So it could be 1, 2, 3, 4, or maybe a positive integer bigger than 4. And then we form n real numbers, x1, x2, all the way up until xn. And then we form the following object, which is called an algebraic vector, and it's denoted as follows. It is x with a line on top. So the line on top means that it's an algebraic vector. And that's equal to, with n components, the first component is x1, the second component is x2, all the way up until xn, and then we have these angle brackets, all right? So this is known as an n-dimensional vector. So that's the definition. So notation is very important in this course, so do not lose marks for bad notation. Now, xi is known as the ith component of vector x. Again, you can see the line on top of x, so you know it is a vector. And then Rn is a set of all vectors of this form, i.e. all vectors with n components whose each component is a real number. That is, vector x is the element of Rn. So we have a beautiful way of notating an n-dimensional vector. So for example, if you look at the vector 3, 7, 8, it has 3 components, so that is a 3D vector, so it's an element of R3. If you look at the vector 5, 4, 0, 3, it is a vector with 4 components, so it is an element of R4. Alrighty. Now, when we have objects, we need to know when objects are equal. So let's have a definition for that. We say vector x and y are 2 n-dimensional vectors, and they are equal if and only if. I hope you've seen this shorthand notation, if and only if, which means the left-hand side implies the right-hand side, and the right-hand side implies the left-hand side. So when are 2 vectors equal? Well, 2 vectors are equal if they have the same size, and each of the components are the same. So the first components are the same, the second components are the same, and until we have that the last components are the same. Alright, this is very important. Alright, when we know when 2 vectors are equal. Let's quickly do this example. Say vector x is this 3-dimensional vector, and y is this 3-dimensional vector. And the question is the following. Find alpha, or find all alpha, so that the 3 vectors are equal. Alright? So let's start the solution. So if vector x is equal to vector y, then the first component of vector x is equal to the first component of vector y, which is 1. The second component of vector x, which is alpha squared, is equal to the second component of vector y, which is 4. The third component of vector x, which is 3, is got to equal to the third component of vector y, which is 3. So we need to satisfy this. Now, 1 is equal to 1. That is always true. 3 is equal to 3. That is always true. So we only need alpha squared to be 4 if vector x is equal to vector y. And the solutions is alpha is 2, or don't forget the negative solution, alpha is minus 2. And that is the answer to this short problem. So there are 2 values for alpha, which makes vector x and vector y the same. Alright, so now we know what an n-dimensional vector is. For the most part of the course, we'll be playing with 2D and 3D vectors. And we also now know when 2 vectors are equal, but we want to do more with vectors. So we've got to have operations. So like you have operations for real numbers, you also have to have operations for vectors. So let x be this n-dimensional vector, and let y be this n-dimensional vector. And Again, notation is important, so we typically put lines on top of the variables to indicate it's a vector. And if you're talking about vector x, the components are x1 all the way up until xn. If we talk about vector y, then the components are y1 all the way up until yn. All right? And let alpha be any real number that you like. All right. So we got to define addition. So if x is an n-dimensional vector and y is an n-dimensional vector, we define x plus y to be a new n-dimensional vector with components x1 plus y1, the second component is x2 plus y2, etc. So, very easy. You just add the corresponding components. Now we also want to be able to subtract vectors. So vector x minus vector y will be, the first component would be x1 minus y1, the second component would be x2 minus y2, etc. So again, you just subtract the corresponding components. And we also want to be able to take an n-dimensional vector and multiply it with a scalar, maybe 2, or with alpha. So alpha times vector x, so x is an n-dimensional vector, alpha x is an n-dimensional vector with components alpha x1, alpha x2, etc. So just each component of vector x gets multiplied by alpha. And likewise, we're also going to define this concept that if x is an n-dimensional vector, then minus vector x is defined as the vector where you multiply each component with minus 1. So minus vector x will be the vector with components minus x1, minus x2, etc. Alright? So if x and y are n-dimensional vectors, then the sum, the difference, multiplying with a scalar or multiplying it with minus 1 are all n-dimensional vectors. And you can see from this definitions that vector x minus vector y is equal to vector x plus this other vector minus y, known as the additive inverse. Alright? So vector subtraction is actually vector addition, but you add minus y, which is vector y multiplied with a scalar minus 1. Alrighty, so there are some special vectors that we have to talk about, and the one special vector is the zero vector. Alright, so the zero vector in Rn is the algebraic vector where each component is 0. Alright, so if you have a 2D vector, then you have 2 components that is 0. If you have a 3D vector, then you have 3 components that is 0. Alright, so the next thing you want to ask is, what properties do we now have that we've defined operations in this manner? Alright, and there's a lot. This is theorem 1.1.9 in the textbook. So if x, y, and z are algebraic vectors in Rn, and alpha and beta are any real numbers, then all of the following is true. That vector addition is commutative. What does it mean? It means that x plus y is the same as y plus x. We'll prove it in a moment. Another nice property is that vector addition is associative, so you can re-bracket. So vector x plus y plus z is the same as x plus y plus z. Zero is known, the zero vector is known as the additive identity. That vector x plus the zero vector is vector x. Minus x is the additive inverse of vector x, because vector x plus vector minus x is the zero vector. Remember, a vector plus a vector is a vector. More nice properties. Scalar multiplication is associative. Remember, alpha and beta are scalars. So alpha times beta times x is equal to alpha times beta times x. So again, I want to emphasize here, if you do the left-hand side, you would start by taking vector x, multiplying with scalar beta, and you form a new vector. Then you would take that vector, you multiply it by alpha. So that is how you would calculate the left-hand side. And the right-hand side, you would say, okay, let's first multiply the scalars, and then take that answer and multiply it with vector x. And it turns out that the left-hand side is always equal to the right-hand side. All right? So knowing these properties are important because it tells you what you can do with vectors. Now, one is a multiplicative identity because if you take scalar 1 and you multiply it with vector x, it remains vector x. So it follows easily from definition. And you can see, by the way, if we define things, minus 1 times vector x is minus x by definition. Likewise, 0 times vector x is the zero vector. If the left-hand side is a vector, then the right-hand side must be a vector. Property 9. Alpha times the zero vector is the zero vector. Property 10. Scalar multiplication is distributive over vector addition. So alpha times x plus y, where x and y are vectors, is alpha x plus alpha y. And 11, scalar multiplication is distributive over vector addition in R, so we can say what it means in an equation. Alpha plus beta times x is alpha x plus beta x. All right. Now, you must be able to prove all of them. And number 10 is in the book. So I'm going to do number 1, and I'm going to start off by saying, okay, what we are going to do here is not for the n-dimensional case, but just for a specific case. If x and y are any 3D vectors, we are going to prove that x plus y is the same as y plus x. All right. Now, proofs are important in this course, and so please make sure you do at least one proof a week so that you are comfortable with this ideas and being able to communicate mathematics. Now, a setup is important. So to start off, let's start off with the following. Let vector x equal to x1, x2, x3, where x1, x2, x3 are real numbers. Likewise, let vector y be y1, y2, y3, where y1, y2, y3 are real numbers. So, knowing the components of a vector is important, and this is why we have this starting paragraph. So, we have a handle on vector x, we have a handle on vector y. All right? So now, let's see if we can prove this. So let's start with the left-hand side. So the left-hand side is vector x plus vector y. Now, by our definition, vector x is a 3D vector with these components. Vector y is a 3D vector with these components. All right? And now we apply the definition of addition. So we know that this vector plus this vector becomes a vector with components x1 plus y1, x2 plus y2, and x3 plus y3. All right. And now we know for any real numbers p and q that p plus q is equal to q plus p. All right. We've learned this in high school. All right. So we're going to apply this fact. So typically when I write a proof, I give my reasons on the right-hand side. So using this fact 3 times, x1 plus y1 is the same as y1 plus x1. x2 plus y2, it's the same as y2 plus x2. x3 plus y3 is the same as y3 plus x3. All right? So here I'm using the property that addition of real numbers is commutative. All right. And now we continue. Now this 3D vector, I can write it as this 3D vector plus this 3D vector. Because we know how to add vectors, we just add component y. So here I'm using the definition of addition of vectors. And that is why I can go from this line to this line. So when you look at proofs, you always ask yourself, why do I go from the previous line to the next line? And by definition, this vector, that is y. And by definition, this vector is x in our starting paragraph. And what is y plus x? That is the right-hand side. And we are done. So knowing that the addition of real numbers is commutative, we are able to prove that the addition of vectors is commutative. All right? But this is the kind of proof that we will expect you guys to produce if we ask it in a semester test. All right? So do practice writing out proofs. All right? Now, likewise, you can prove all of the other properties listed on page 6. Alrighty. So guys, we're getting towards the end of the video. So please do example 1.1.10 on page 7. All right? The more you practice, the easier this stuff will do. And also do the exercises in the textbook, all right, to get familiar with vectors, all right? So we are starting this course with vectors, and we're not just going to do vectors in chapter 1. Vectors, we will also be revisiting vectors and doing even more nicer things with vectors in chapter 5, all right? So make sure you're familiar with vectors. And thank you for watching this video. Please tune in for the next video on chapter 1.2. Have a lovely day. Bye.